The topic that we are going to discuss is addressing modes. Addressing modes means where are we going to bring the data on which we are required to perform the operation to execute this particular instruction. The data that can be the data over which the operation is required to be operated in an instruction can be brought from several locations. One location can be a register, another could be a memory, or another could be a input. So depending upon where we are bringing the data from, the addressing modes are divided into several types. The first addressing mode that we are going to discuss today is implied addressing mode. Implied addressing mode says that everything is explained in the instruction itself. Let us understand it with an example. Let us suppose CMA. Let us take up an example of CMA. CMA is complement accumulator. Complement accumulator instruction says that the content in the accumulator, the data in the accumulator is required to be complemented. Whatever data is put in the accumulator is required to be complemented, and the result is to be stored back to the accumulator. STC, set carry. We have to put STC instruction when executed will put 1 in carry. CMC is complement carry. It will complement the contents in the carry. If the contents of carry are 1, they will change to 0. If they are 0, it will be changed to 1. XCHG. XCHG instruction is a data transfer instruction in 8085 which says that the contents of HL and DE will be exchanged. So in these instructions, everything is implied, where the data is, what is the source of the data, what is the operation of the data, and what will be the destination of the data. The next is immediate mode. Immediate mode, as we have discussed many times, immediate mode is whereby the data will be the part of the instruction itself. Whenever an instruction has I in it, it means it's an immediate instruction whereby the source of the data will not be a register, not be a memory, but it will be the data itself. For example, MVI R, data, the data specified in the instruction is required to be moved to register R. ADI data, move the data that is the part of the instruction to the accumulator, storing the result in accumulator. SUI data, subtract the contents of accumulator from subtract the contents of data from the accumulator, storing the difference in accumulator. LXI RP data 16, the 16-bit data is required to be loaded into the register pair specified. The third category is register direct mode. Register direct mode specifies that the source of the data would be a register. The data will be brought from the register. Move A, B, move the contents of register B to register A. So the data is coming from register B. So it's a register direct mode. Add B, the address of the data is register B here. Add the contents of accumulator to register B, to the contents of register B, storing the result in into the accumulator. XOR A, XOR the contents of accumulator with the contents of accumulator, storing the result back in accumulator. The fourth category is register indirect mode. Register indirect mode says that now whatever is written here, for example LDAX RP, now here this register pair is not the source of the data, but it is actually acting as a address of data. So now when LDAX RP is required to be performed, first the contents of the register pair will act as the address, and now we will go to that address and bring the data, and then the required operation will be performed here. Same in STX RP. This is register indirect, this is register direct mode, whereby the content were coming from the register itself. Register indirect mode, whereby the contents are now not coming from the register, but the register is acting as is holding the address of the data. So we are required to go to that address, and then we will bring the data from there. This is register indirect mode. Direct address mode, whereby now, for example, a direct address mode, LDA address, add address. LDA address instruction says that there the register is not giving, let's do it again, LDA address. LDA address says whatever address is given here, go to that address, bring the data and load it into the accumulator. Add address, this is not a 8085 instruction, but this is available in some microprocessors and microcontrollers. This instruction says that you are required to add the content of accumulator with the contents that are placed on this address. So go to this address, bring the data from there, add it to accumulator, store it to the accumulator. So now this is the direct address mode, where the data, where you are given the address itself in the instruction. Sixth is indirect address mode. This instruction says that whatever address is given in the instruction is not the address of the operand, but now you will go to that address. On that location, you will get another address. You are required to go to that address and you will get the data. For example, I had 25 written in this instruction, whereby when I go to 25, I get 32. Now 32 is not the operand, it's not the data, but it's the address. I go to that address and I get the data. If it would have been direct address mode, I would have gone to 25 and 32 would have been the data. But this is the indirect address mode, where going on to 25, I will get another address on which I have to go and then I will get the data. The relative addressing mode. Relative addressing mode says that the instruction is written as rel add 50. This is not part of 8085 instruction set, but still this comes in. There are several microprocessors which have such addressing modes. So now relative addressing mode. Relative addressing mode says that let us suppose that on 5904 instruction is written as relative add 50. It's a 2-byte instruction. So the PC would be storing the next instruction on 5906. How the address would be computed as 5904, on 5904 relative add 50 is written. PC is now holding, since it's a 2-byte instruction, PC is now holding 5906. Okay, the address computation when this instruction would be executed would be done how? EA equals to 5906, whatever is stored on PC. 50 will be added to it, and the content now PC, the address now PC will stored would be 5956. So this instruction actually changes the address, whatever address PC is storing. 5906 plus 50. If it would have been written 25 here, 5906 plus 25 would have been done. If 100 would have been written here, 5906 plus 100 would be done, and the resultant address will be stored on PC. Eighth type is indexed and base addressing mode. First we will discuss indexed addressing mode. Indexed addressing mode, you will not find such instructions in 8085, but as I have already said that we are studying the generic addressing modes. So these are available in certain and many microcontrollers. Indexed and base addressing mode. Indexed addressing mode. Effective address, EA stands for effective address, equals to index register plus offset. For example, let us suppose it's an array where we are storing a 2-byte word length. The word length is 2. So the element first will be stored on 10th and 11th location. Each content will occupy 2 bytes. Okay, so now A2 will be storing 2 locations, A3 will be storing 2 locations. So every element in the array is storing 2 locations. So the size of the element is 2. So now if the address of this array is what will be done is if this is stored on 10th, then the next element will be stored from 12th. The next element will be stored from 14th. The next element will be stored from 16th and onwards. This is indexed addressing mode. This specifies the index, and you've done the array, the index of the array. Okay. So it's adjusted according to the word length size. If it's an integer 2 byte, character 1 byte, the next would be stored on, if it's a character type array, then if the first element is being stored at location 10, then the next element will be stored at location 11, 12, 13. If it's an integer type array, then first element is stored at 10, then the next element will be stored at 12. If it would have been a float, which is storing a 4 byte, the word length is 4 byte, then the first element will be stored at 10, and the next element will be stored at 14, and the next element would be stored at 18, so and so forth. Now we'll study base addressing mode. I have a program which is program XYZ, which is stored from 1000 location. The starting address of this program is 1000. Okay, it has been loaded at 1000. It stores total 500 instructions, so the program XYZ ends at 1500. Okay, now 500 and 500 total 500, so it would be storing 1499 total 500, since it's starting from 100. The program XYZ ends here. Okay, so now the starting address is 1000, program XYZ, and the size of the program is 500. What the operating system will be storing as, what will be stored as, and how the next address computation for the next program will be done. The address computation for the next program, if the program size of XYZ is 500 and it is being stored at 1000, so the base address of XYZ would be 1000 and offset would be 500. Whenever I wish to store another program, the second program, it would always be stored at 1000 plus 500. Okay, so it would be 1500.